take is Holocaust sensors. Before going to the details of the sensors, I want to explain something about the magnetic field, power bank, and roller force like that. Magnetic field is generated whenever a charge carrier such as electrons falls to a space or an electrical conductor. And the power magnet is like it's a kind of a source of the magnetic field. This is a type of a power magnet. Here you can see it has an output and a south pole, and these are the magnetic field lines which are surrounding the power magnet. And the magnetic field lines start from the north pole and it ends in the south pole. The power magnet has an north pole and a south pole, and the magnetic field lines will be stronger in the poles, and if two power magnets are folded like this, then if they are the light poles will repel each other and unlike poles will attract each other. So these are very common things which we already know. Now I would like to explain about the Lorentz force. Whenever a carrying conductor is placed in a magnetic field, it will experience a force which is known as the Lorentz force. So it can cause some variation to the charge carriers, because whenever a Lorentz force is acted, whenever the Lorentz force comes into act, the charge particles will displace from its initial position, and they will try to accumulate inside the conductor. So if a particle of charge Q moves with a velocity v in the presence of an electric field E and a magnetic field V, then they will experience a force F, which is given by F is equal to Q into E plus V cross V. The term QE stands for electric field, and the term Q into V cross V is called magnetic field. The direction of this Lorentz force is given by the right hand thumb rule. Here, this is the velocity of the particle, and this is the direction of magnetic field, and this is the direction of Lorentz force. The right hand thumb rule is like this. If we hold the thumb in the direction of velocity, and the middle finger will point in the direction of Lorentz force, and this finger it will point in the direction of magnetic field. It's like this. If you point the thumb in the direction of velocity and this finger in the direction of magnetic field, and then the direction of middle finger will give the direction of Lorentz force. So we can find the Lorentz force. It is given by V into V cross V. And now I would like to explain what principle of Hall effect, that is Hall effect. Because long back in 1879, Daniel Scott first observed the Hall effect. What he did is he took a rectangular slab to which he applied a perpendicular magnetic field, and he applied current also in the direction perpendicular to the magnetic field. So when he measured the potential across the conductor, I mean the rectangular slab, he found that a potential is developed across the conductor. That potential is actually known as the pole voltage. So from that he concluded that whenever a current is passed through a sample kept in a magnetic field, a potential will be developed which will be proportional to both magnetic field and current. So the direction will be perpendicular, and this effect is known as Hall effect. I want to explain in detail about theory of Hall effect. Here this is a conducting slab in which current Ix is passed in the x direction, and the length of the conductor in the x direction is L, and the width of the conductor is W in y direction, and the thickness will be T in z direction. And this conductor is assumed to carry charge carriers, Q number of charge carriers, and the velocity is V. So let's now assume that this conductor we take into a magnetic field. A perpendicular magnetic field is applied. We take this conductor magnetic field, and its direction will be along z direction like this. Vz is the magnetic field. So like I said before, whenever a current carrying conductor is placed in a magnetic field, it will experience a force which is known as Lorentz force. That Lorentz force will be experienced by this conductor, and due to the Lorentz force, the charged particles will try to deflect in both directions. So they will try to accumulate on the sides of the conductor, and due to the accumulation of these charge carriers, an electric field will be developed in a direction perpendicular to that of magnetic field. direction, the electric field will be in such a way that as the time passes, the electric field will try to neutralize the magnetic field. So after some time, a steady state will be reached. Then the Ey will be equal to V into Vz. We can show derivation for this, and when steady state is reached, Ey will be equal to magnetic field. That is, electric field will neutralize the magnetic field, and this electric field is known as a Hall field. And if you want to calculate the Hall voltage, we can integrate this electric field over the bridge from 0 to W, and we can arrive at the equation like this: Hall voltage is equal to minus Ey into W. This is another diagram which shows Hall effect. Here no magnetic field is applied, and when the current is allowed to flow through this rectangular slab, the current will be linear. And if you try to measure the potential difference across this, the voltage will be zero, since no magnetic field is applied. And this is the case in which we apply a perpendicular magnetic field. If you apply perpendicular magnetic field, the current will become non-uniform due to the Lorentz force. Since the Lorentz force will try to deflect the particles, the current will become non-uniform. And now if we take the potential difference across this, we can find out the Hall voltage. The Hall voltage will be developed across this. If you can see, both the current and magnetic field will be in perpendicular directions, and the Hall voltage will be perpendicular to that. And what a Hall effect sensor does is, it's actually a transducer that can vary voltage in response to a magnetic field. So it can sense the magnetic field, and as a response it can give voltage. So whenever changing magnetic field occurs around a Hall element, it produces corresponding changing Hall voltage. The sensor is made in such a way that it can sense both the magnetic field and the voltage. These are some of the features of those devices which use Hall effect sensors. They will be having longer lifetime, and the speed of operation will be very high, over 1000 kilometers is possible. They will be having no moving parts, and the temperature range will be very wide, like from minus 40 to 150 degrees centigrade is possible, and their operation will be always repeatable, highly repeatable operation. This is a general sensor based on Hall effect. This is general sensor based on Hall effect. In this diagram, we are having, this is actually the Hall element. This is the Hall element. Actually, the Hall element is constructed from a thin sheet of conductive material, with output connections perpendicular to the direction of current flow. So whenever it is subjected to a magnetic field, it responds with an output voltage proportional to the strength of the magnet. This output voltage may be very small. It will be very small in the range of microvolts. So it requires additional circuitry, like additional electronics, to achieve a useful voltage level. So when the Hall element is combined with the associated electronics, a Hall effect sensor is actually formed. So in a generalized sensing device, the Hall effect sensor senses the field produced by the magnetic system. The magnetic system responds to this physical quantity to be sensed through the input interface. And the output interface, the function of the output interface is to convert the electrical signals which are given by the Hall effect sensor, and take it to useful applications. So that is a function of output interface. So all these elements are combined. When all these elements are combined, they will form the Hall effect sensor. This is a diagram of an analog Hall effect sensor. In this, we are using a voltage regulator, a Hall element, and also a differential amplifier. So a voltage regulator is used to regulate the voltage, and the purpose of using a differential amplifier is to amplify the potential difference. So actually, the voltage produced by the Hall element will be very low. They should be signal conditioned. For that purpose, we are using an amplifier. So instead of a differential amplifier, if you use some other amplifier, there can be another purpose. If you take the voltage with respect to this terminal and the ground, then the voltage measured will be the common mode voltage. It's always present there. So if some other amplifier is used, it will amplify the common mode voltage. If we use our aim is actually to amplify the potential difference only. So if you use a differential amplifier, it will only amplify the potential difference. So that's what we want to do. So that's a function of an analog feedback sensor. And there can be some other problem, like the magnetic field can vary from positive to negative. So the output of the amplifier will be obviously positive or negative. So in that situation, we will finish and this will be like we want to use two power supplies for taking positive and negative voltage. So in order to avoid that, we are using a null voltage. So we will when the magnetic field is zero, the output of the amplifier will be this null voltage. If positive magnetic field is applied, then the output voltage will go beyond this null voltage, and after some time it reaches a saturation level. Like that, when negative magnetic field is applied, it will go below the null voltage, and after some time it will reach a saturation level. And this is a transfer function, and this is actually the graph between input magnetic field and output voltage. The readings are taken for various voltage levels like 5, 8, 10, and the variation of magnetic field is shown like this. Actually, the main characteristic of this transfer function is sensitivity. It is defined as the change in output whenever a change in input occurs. So it is actually given by the stop of the characteristic. And null offset is the output of the sensor when no magnetic field is present. Here it is that voltage is 0 volts. So span gives the range of output voltage of the analog output sensor. And next one is a digital feedback sensor. It's very similar to analog feedback sensor. The only difference is that here we are using a split trigger. The reason for using the split trigger is that the output of the digital feedback sensor will be either on or off, like 1 or 0, like that. So whenever an output comes out of the amplifier, the split trigger will compare that output with the reference value. If the value at the output of the amplifier is more than that reference value, then the split trigger will be turned off. That will turn on the sensor, and if that value is below the reference value, then the split trigger will be turned off. So like in that manner, the sensor will be switched on and switched off. Like that, in that manner, the feedback sensor works. Okay, and this is the transfer function. Here we are increasing. Even if we increase the electromagnetic field to some extent, it will remain constant until a point known as operating point is reached. When the operating point is reached, the output of the sensor will switch from off state to on state, and even if we increase the magnetic field beyond that extent, it will still remain in that constant stage. So what we can do is just decrease the voltage just below the operating point, and after that a point known as release point will be reached. At that stage the sensor will switch back from on state to off state. That's exact working of a digital feedback sensor. Next one is the vane operated positive sensors. Here as this diagram it consists of a magnet and a digital feedback sensor. There is a gap in between the magnet and the feedback sensor, and this gap is where we are passing the vane, so that the main function of the vane operated positive sensor is to detect whether the vane is present in that gap or not. This is how the vane can be moved through this gap, and the magnet is present here and the feedback sensor is here. And here we are adding more pieces to this, and working is like this. When the magnetic flux lines start from the magnet, and they will cross the gap, and they will reach at the south pole of the feedback sensor, and actually the north pole is on the magnet. So in the normal case, when the vane is not in this gap, the sensor will remain on. When gone position because the magnetic flux lines are undisturbed. So the sensor will remain in gone position. So whenever a wave is passed through this gap, it will cut the magnetic field lines in such a manner that the sensor will be turned off. So like that, we can find out whether the wave is present in this gap. This is actually the design of wave operator sensors. First of all, we should actually make a concept. We should design that concept, and after that, the design of the wave should be made. When we make the design of the wave, the considerations that we take are the wave material. The material used must be magnetically soft and free of magnetization. Usually, for this purpose, their low currency is only and wave thickness. Wave thickness should be always be optimum, and the dimension and tolerances should be such that it should give accurate result. The sensor should be very accurate. And after that, we should develop the input inputs for developing that. The considerations we are saying is centering of the wave in the gap, allowance of entry and runout, and provisions for initial positioning of the wave related to the sensor. After doing all these things, the design of input interface is over. And the next step is to develop the output interface, and the final step will be like we should design sensor on the breadboard, and after that the final step is to integrate all the weight sensor and the output interface in the system, and the final step is to test the completed sensor. Like that, the design of the digital sensor qualities and electromagnet and a Hall effect sensor. So the function of the electromagnet is like this. Whenever a current is passed through the electromagnet, it will produce magnetic field. That magnetic field will be sensed by the Hall effect sensor. So that the magnetic field produced will be like will give the amount of current passing through. So it's like the magnetic field is a function of the current passing through the device. And also there is a significance of the shape of the electromagnet which can be used. If the shape of the electromagnet is like a coil, then it will give more magnetic field. Like when the current is passed, the total magnetic field will be equal to the number of turns of the coil, the product of the number of turns of the coil and the current passing through the current. This is actually the transfer function of that sensor. When the current is I2, the sensor will be in the on position, like it is in the operating position. And when the current is decreased to I1, it will be in off position, like it is in release mode. That is known as release mode. The design of this sensor is actually very simple because it is already a complete sensor. The only thing we have to worry about is we should choose a proper current sensor and a good output interface. That's the only thing we should do. And these are the specifications. It should be operated within a range of 5 to 25. The current should be like that, and the maximum continuous current, that is the maximum current which can be used for this sensor in any application. It should be around 20 ampere, and maximum coil resistance is used for measuring the voltage drop across the coils, and also the power dissipated. It should be around 5 milliohm, and the temperature stability actually gives the variation of operate and release points. How much they are varying according to temperature. That is given by temperature stability. Next one is linear current sensor. Actually, the linear current sensor consists of a ferrite or silicon steel. You can see both the core and IC are accurately mounted in a plastic housing. The current passing through the conductor being measured generates a magnetic field. So the core captures and concentrates the flux on the Hall effect IC. So the linear response and isolation from the sensed current makes the linear current sensors ideal for motor control feedback circuits like in many other applications. So the voltage output of the Hall effect IC is actually proportional to the current in the conductor. So the linear signal accurately duplicates the waveform of the current being sensed. is the waveform of the current sensor, and when there is no current, we will be getting 50% of our VCC as output voltage, and when the current is increased, it will reach around 75% of our VCC. When it is decreased, it will reach till 25% of our VCC. After that, it goes to saturation. So the design of this sensor is very similar to that of our main operator sensors. So I don't want to explain that in detail. So the only difference is that we are considering some other factors like the transfer function, resolution and accuracy, frequency response, output conservation, conversion, either from output like that and output compensation like that. Some additional calculations are available. Rest is all similar to main operators. And the specifications are like this: its supply voltage should be from 6 to 12 volt, and supply current should be about 20 milliampere. Offset voltage should always be VCC by 2, and offset shift is always plus or minus 0.02, and response time is 3 microseconds. And next one is mechanically operated solid state switches. Actually, from the figure, it consists of a modified sensor and a plunger magnet. So the main function is actually when the north pole, for a normal off switch, when the north pole is nearer to the sensor, it will be in off switch. So in order to turn on the sensor, we should reverse polarity. Actually, the south pole should come near the magnet, then only it will be turned on. So also in the reverse direction also. Normally on switch will result from the reversing of the magnetic field. So the south pole is normally opposite to the digital output of our sensor and maintaining the switch in a normal on state. So when the plug is depressed, the north pole is about near the sensor, turning it off. So that's how it works. It is almost in many applications it is used as a switch. So that's the main purpose of using it. These are some of the specifications of the mechanically operated solid state switches. The free travel is the distance the switch plunger moves from free position to operating mode, and operating mode is the mode at which all operation starts, and overtravel is the distance how much more the plunger has traveled after going past the operating mode. That is what is overtravel, and differential length is the distance between the operating point and the release point. Operating force is a mechanical force which is necessary to depress the plunger. So all experiments are showing there. Next one is flow rate sensor. Actually, the flow rate sensor consists of a digital output sensor through which the water is going to flow, and consists of a magnet which is used for sensing the flow of water. So this figure shows the concept that uses a digital it actually uses a digital output bipolar sensor, and the magnet is mounted to an impeller to measure the flow rate for water softener. So in this design, the softener can be made to automatically recharge on demand instead of a timed basis. So the demand is determined by measuring the amount of water that has to be passed to it, and when a certain level is reached, the recharge cycle actually starts. So you can show in the figure. There are even if we use various methods, the principle is always the same. The general principle is like for each actuation of the sensor by a magnet or by shunting the magnetic field corresponds to a measured quantity of water. In the example shown, the magnetic field is produced by magnets mounted on the impeller blade. That's they are the impeller blades, and the impeller blade is turned by the water flow. The sensor produces two outputs for evolution. Like that it functions. All depends on the impeller blade function. And next one is sequencing sensors. These are like these are sequencing or duration of number of operations. The duration can be achieved by different kinds of mechanical operations. One is shown in this figure. Here, a number of ferrous discs or cams are mounted on a common shaft, and the discs are rotated and the gaps of the modified coincidence. The disc rotating in tandem with this main is used to create a binary code, which can establish a sequence of operations. So the program will be altered by replacing the disk one after the other according to some convention. So that can be used for that purpose. That's the function of a sequencing sensor. And in read as a read speed sensor for testing purpose. This is the reference voltage in optical. Yeah, we are using an optical encoder.